time constant. So when we're working with when we have a capacitor and a resistor in series, that resistor is going to have the opposition to the current and stuff, and it's going to slow the amount of time that it takes to charge that capacitor. So here I just kind of built up a circuit where we can switch it, we can apply the power to it, and then we can switch it, and then we can eliminate the power supply, and then the capacitor is going to become the source. So let's just take a look at it. Like always, we kind of analyze our circuits. We like to draw our current paths and polarities. So right now, with the switch being in the neutral position, nothing's really happening going on with the circuit. But the instant I go ahead, the instant I turn that switch on, and I bring power to my RC circuit, my capacitor is going to act like what? Short or an open?
Short.
It's going to act like a short. So what's going to happen is that my current is going to come out of my source. This wire, there's nothing going on with this wire. That's not connected, so that's not, even though I have a current node, there's no current going through there. So all my current is going to come up, go right through my capacitor, because that's going to act like a short. And then it's going to go through my resistor, and then back into my source there. So what's going to happen is that the instant that and this is on this graph here, yep, thank you, on 410. So what's going to happen is that I'm going to get this charging curve. Okay, so, and this is very predictable. It doesn't matter what I have for a capacitor value or a resistor value, my capacitor is going to start to charge. And it's going to charge up to 63% of its capacity in what we call a one-time constant. And then as I let that time go on, after two-time constants, it's going to charge up to 86%, up to 95%, then up to 98%, and then up to after five-time constants, it's going to be almost fully charged. The capacitors, because of the internal leakage that we have in the capacitors and stuff, will never get up to 100%. If I let it keep on going, it'll get very close to 100%, but it'll never really get to 100% because of the internal leakage of the capacitor. So we consider that after five-time constants, that my capacitor is going to be fully charged. So to figure out what a time constant is, my time constant is just going to equal to my resistance times my capacitance. So I have on my circuit here, I have a 10 kilo ohm and a 22 microfarad capacitor. And what would my time constant be equal to? If I just multiply those two off, what would I get? What'd you say? 22
whatever.
Milliseconds, yep, because it's in time. Yep, so it's going to be 22 milliseconds. So what that's saying is that when I hit that switch for the first instant, my capacitor voltage is going to be at 0. It's going to start at 0, and then in 22 milliseconds, it's going to get up to 63% of its charge. If I keep that switch closed for another 22 milliseconds, give me a total time of 44 milliseconds, then it's going to charge up to 86%. Then at 66 milliseconds, it'll be charged up to 95%. 88 milliseconds will be charged up to 98%. And then after it would be 102 seconds, then it charge up to
104.
Being fully charged at 99%. So then once that capacitor acts like once that capacitor fully charges up, all my voltage is going to be measured across my capacitor, and that capacitor is going to act like an open, and then my current is going to stop flowing after 5 time constants. So after 102 milliseconds, the capacitor is fully charged, and the current is going to stop flowing. Then, if I go ahead and if I close my switch, or move my switch to the other position, then what's going to happen is I'm going to remove this source, and now since my capacitor is fully charged, it's going to act like its source. So now the capacitor now just became the source. Before it was taking all the energy and storing it, I hit the switch, now my capacitor now becomes the source. And then what's going to happen now is that my current is going to start flowing in the opposite direction. Now my current is going to start flowing through here. It's going to go up through here. Across my resistor, now you can see that the polarity across my resistor has changed. And so now just the opposite is going to happen. So that same rate that the capacitor charged, the capacitor is going to discharge across that resistor at the same amount of interval. So now my capacitor is going to, after 1 time constant or after 22 milliseconds, my capacitor is going to start to discharge to 37% of its value. And then after 44 milliseconds, it's going to drop down to 14%. And then after 5 time constants, or 102 seconds, that capacitor is going to what we consider totally discharged after the 5 time constants. And then there's not going to be any energy left in there. The voltage across the capacitor is going to equal 0. The current is going to stop flowing. And then the resistor is going to drop down to 0. Since there's no more energy left in my circuit. Alright, so any questions on that? Does that make pretty good sense there? Alright, so these are our time constants. It's just a matter of, what is the resistor value, what's the capacitor value, just multiply those two out, and that's going to be the equivalent to the 1 time constant. Alright, so then we'll change up the circuit a little bit. We'll keep the same values, but we'll change up the circuit. Then we can simulate the same circuit and simulate the switch by using a square wave. So I'm going to change out my DC power supply, and I'm going to put in a square wave in there. Now when we're putting in a square wave, and we're working with a circuit like this, typically when we're working with square waves or pulses, for most applications, we're going to have that DC offset in there. So what we want our square wave to be is we always want our square wave to be at a reference of 0 volts, have a DC reference of 0 volts, and then we're going to go up to a plus 10 volts. Draw 2 waveforms here. So now when we put in a square wave in here, what we always like to do is we like to analyze the first half of our cycle. So from here to here is going to be my first cycle, and then this is going to be my first half of my cycle, and then from here to here is going to be my second half of my cycle. So that's going to be my 1 complete cycle. So we're going to analyze the first half of the cycle, and we're going to have it, and it's going to go up to a positive 10 volts. So the polarity across my function generator is going to be plus and minus. And it's going to have a voltage of 10 volts. So now my current is going to start to flow. My capacitor is going to act like a short. Polarity across the capacitor is going to be negative, positive. The current is going to start flowing through the resistor and then back into my source. So now so this is going to be my source. So when we're graphing, we kind of keep everything off to the left-hand side. We label what it is. You know, this could be DS1, whatever you want to call it. We put in our DC offset, and we also put in what our peak voltage is. So there's our signal going in, and then we're going to analyze and see what the signals look like coming out of here. So we're going to have so when we hook up our oscilloscopes to the circuit, we'll have channel 1, and then our reference point is going to be the ground. So our probes are going to hook up to our reference point, which is our ground. So channel A is going to be my source. So this is going to, or my test point A is going to be my source. We could DS1 or my test point A. Test point B is going to be my capacitor. So I'm going to have C1, DC1 or test point B. And that's going to be on channel 2. So now we're looking at what's going to happen when I first send in that square wave. And we'll say that my square wave for a total time for one complete cycle, we'll say is make sure. There's going to be my total time for one complete cycle, we're going to say is going to be 220 microseconds. One half of that cycle then is going to be 110 microseconds. So when you're looking at our time constant, for 5 time constants, that should have been 110 microseconds, not the 102 that we're using. But it's going to be 110 microseconds for one half of that cycle. So that 110 microseconds is going to be equivalent to my 5 time constants. So we know that we're going to charge up the capacitor up to its full capacity at 5 time constants. So what's going to happen then is that if I'm measuring and I'm watching the voltage on channel 2 and watching the voltage across that capacitor, and I'm lining it up with my voltage source, and so what I'm going to see on my capacitor, this thing is going to go from 0 volts, because when I first applied the power to it, once that signal came in, that first positive pulse came in, my capacitor acts like a short, so it's going to start out at 0 volts. And then it's going to start to charge up to its full capacity after 5 time constants. Okay, so that's going to be equal to my 5 time constant. And so as I'm watching that voltage, that capacitor is going to start to charge, then it's going to act like an open, and then it's going to take all of its voltage. And so it's going to go up to, from starting out from 0 volts, then it's going to go up to my positive 10 volts. And then at that point, then all the current in my circuit is going to stop. So now, if I took the difference between channel 1 and channel 2, did my math function on there, and I watched the voltage across my resistor, so now my VR1, or the difference between channel 1 minus channel 2, or test point, yeah, and that would be test point A to B. Okay, so from test point A to B, it's the difference between my channel 1 and channel 2. The minute this signal came in, this capacitor acted like a short, so it didn't take any of the voltage, so what would be my voltage across R1?
The full 10 volts.
Would be the full 10 volts. So my voltage of my resistor is going to start out at its 10 volts. Then as the time goes on, the capacitor starts to charge, and it's going to start acting more like an open. And it's going to start taking all the voltage. So as the time goes on then, and as that capacitor starts to charge and start taking all the voltage, then the voltage across R1 is going to kind of start to drop. Then after 5 time constants, the capacitor is going to act like an open. All the voltage is going to be across the capacitor. The current is going to stop, and then my voltage across R1 is going to be at 0 volts. Okay, so it's going to be just kind of the opposite of what this signal here looks like. So that's our first half of our cycle. That's what it would look like up here on our oscilloscope if we had our oscilloscope hooked up to it. Then after 5 time constants, my square wave is going to transition from a positive 10 to 0 volts. And when it goes down to 0 volts, that's just like me having my power supply shorted out. 0 volts is the point of reference. So if I have 0 volts coming out of my power supply, I essentially just tied it to ground. So now we're analyzing our half of our cycle there. And once that source goes down to 0, then what's going to happen is that I don't have any more of this sources out of the circuit now, and that capacitor is going to take over. That capacitor is going to take all the energy it stored on the first half of the cycle and return it back into the circuit. The polarity across the capacitor still remains the same, but my current flow is going to change. Now my current is going to flow through here. It's going to go right through my source, down over to here, through my resistor, and then back into my capacitor. So the minute this thing transitioned from a positive 10 to 0 volts, then my capacitor becomes the source now. What happened to my voltage across my resistor? What's my voltage across my resistor going to be?
2 + 2.
So here's my capacitor becomes my source now, and that's charged up to how many volts? 10 volts. So that's my source. Once that transition from a positive 10 to 0, the current starts flowing. So what's going to happen to my voltage across my resistor? What would I have for voltage going across the resistor then? 10 volts. And it's going to be, now before, on the first alteration, it was positive negative. Now it's going to be negative positive. The polarity across my resistor has changed. So it's going to be actually now, if I'm doing the difference between channels A and B, my resistor is going to have a negative 10 volts. So what's going to happen is that this thing is going to, and the minute I close that switch, it's going to take all the source voltage, and it's going to go and shoot down to a negative 10 volts. Now, while well, this becomes the source. There's only a certain amount of energy that this capacitor can store, and that's depending on how big of a capacitor we have, how many farads does it, will be determined how long it would stay charged for. So this thing is going to start to discharge at 22 milliseconds for each time constant. And so after 5 time constants, that capacitor is going to be totally discharged. So that capacitor is going to start to discharge, and it's going to drop down to, after 5 time constants, it drops down to 0 volts. So as this capacitor starts to discharge then, and the voltage starts dropping across the capacitor, so does my voltage across my resistor. So now my voltage across my resistor is going to start to go back to 0 volts. Then if we went ahead and we just drew in our other 2 waveforms, because when we're graphing out waveforms, we always like to graph out 2 complete cycles so somebody can see where the cycle starts to repeat. So then I transition to a high, the capacitor is going to charge up, then it's going to transition from a high to a low, and then my capacitor is going to discharge. And then what's going to happen on this one, it's going to be the same thing. My capacitor then, once that capacitor acts like a short, my voltage across my resistor is going to go up to 10 volts. As my capacitor starts taking all the voltage, it's going to drop down to 0. Then that capacitor is going to act like the source. And then my resistor is going to drop down to a negative 10 volts and then back up. So you can see that from here I have 0 to 10 volts going across my capacitor, but across my resistor now I have a plus 10 volts and a negative 10 volts. Now I have a voltage potential of 20 volts. So I actually doubled my voltage because that capacitor actually took in all the energy on the first half of the cycle and then put the energy back into my circuit on the second half of the cycle. So I get a peak-to-peak voltage of 20 volts. But it never happens instantaneously. I would never really ever actually get 20 volts at any given time. At any given time I would have, because my reference is at 0 volts, I'd have a plus 10 at one time, then I'd have a negative 10, then plus 10, negative 10. So the plus 10 and the negative 10 doesn't happen all at the same time, so I never really get my true potential of 20 volts. But I am swinging that resistor voltage from plus 10 to negative 10. And so then when we're, then the other thing I would like to do then, so when we're graphing then, what we like to do is we like to describe what's going on and what's happening with our time for all these waveforms. So we like to kind of keep these things all lined up. And so my first half of my time cycle is going to be from here to here. That's going to be my 5 time constants. It's going to take 5 time constants to charge up my capacitor. And that's going to be my 110 volts, or 110 milliseconds. My second half of my cycle then is going to be here, and that's going to be another 110 milliseconds. Or equal to 5 time constants. Then my total time then is going to be my 220 microseconds, or 10 time constants. So it always takes 5 time constants to charge, 5 time constants to discharge, and then a total time of 10 time constants, or 220 milliseconds, to totally charge my capacitor up once and then discharge it once. And so we like to describe, what is it taken for time, for what's happening with these times. So what's the frequency of this? Particular circuit then? What's the frequency of my square wave? Anyone know what my frequency would be on this one? How do I calculate out frequency? What's the formula for frequency? Yeah, 1 over the period. So frequency is equal to 1 over
200.
my time. And what's my time going to be equal to for my period?
220 milliseconds.
220 milliseconds.
4.545 hertz.
4.545.
545.
454, did you say, Bob?
4.5.
4.5.
4.5455.
4.545.
Yeah.
5. 5.
And that's going to be in
Hertz.
hertz. No, I don't think it's in hertz, is it? Or in kilohertz. I think it's just hertz.
Hertz.
Yeah. It really hurts.
Are we doing this milliseconds, microseconds? Or we doing-
Milliseconds.
Okay.
So yeah, so if you take 220
We
milliseconds.
kept changing it. We started with micro, and then when...
Did I start with micro? I thought I always was that
Yeah,
milli.
you said micro before.
Oh, did I? I'm sorry.
Yeah.
Yeah, I've been writing milli. I didn't mean to say micro. Sorry about that.
So is this all correct then?
Yeah, it's all correct.
Alright.
Yeah, I said micro, but I didn't write milli. I meant milli. Sorry about that. I didn't catch that. Yeah. Oh, okay. So yeah, after 10 time constants, 220 milliseconds,
That's your 5 times.
and that gives me my 10 times constant.
So if you have 10 times constant.
Yeah. So what point did I say over here? I said.
Yeah, we said over there.
We started over there with micro.
Oh, sorry about that. I didn't.
Yeah, I don't worry here.
I know. All right. So did that? Even though I screwed up on, I mentioned micro, but I guess I meant to say milli. But does anyone understand what that? What is? Does anyone understand that circuit there? Does anyone understand that? Okay. So if I were to change this, and if I only had my first pulse was only at 22 milliseconds, that would be only one time constant, and then my waveforms would be changed because at 22 milliseconds then my capacitor would only charge up to 63%. So that means that if I were to change up that waveform, I don't want to try to do the whole thing here, but let's. So I'm going to change. So we're going to change it up to. This is all going to stay the same. So now if I have my first alteration is only 22 milliseconds. I'm high for 22 milliseconds, then I'm off for 22 milliseconds. I'm going to have a total time of 44 milliseconds. And if I only give it one time constant beyond, then what's going to happen is that the capacitor again is going to start out at 0. And then it's only going to go up to 63% of its charge. Or positive 6.3 volts. Okay. So if I don't have enough time constant in there, then I'm only going to charge up to the amount of percentage that's on my chart. So if I only give it one time constant, it's only going to charge up to the 6.3%. And then when that switches back up, it transitions from a high to a low, even though my source is at 10 volts still, my capacitor only took in that 6.3%, and then it's going to discharge to 37% of that. of my initial voltage there, that 6.3% or 6.3 volts. So I'm going to discharge to 37% of that. So it will be 37% of 6.3. .331 volts. So it's going to discharge down to only 2.331 volts. And then when I transition again now from a low to a high, then it's just going to go up to the 6.3 volts and then discharge down to the 2.31. So it's never going to get down to my 0 volts. It's going to stay from 6.3 volts to the maximum down to 2.331 volts. And so then my voltage across my resistor then, is only going to go up to positive 6.33 volts. And then it's going to discharge down to the 2.331 volts, then go down, and again, as we just kind of keep on repeating our cycle, then this thing is going to go down to the polarity is going to switch. It's going to start out at the 2.331 volts, and then once the capacitor becomes the source, the voltage across R1 is going to go to a negative 6.3 volts, and then that capacitor is only going to charge up. It's only going to discharge to the 2.331 volts, and so this thing is only going to discharge. Since the polarity changed across it, is going to change to 2.331 volts. Then it's going to go up to the 6.3 volts. And then just kind of start repeating the cycle again after that. So we don't give it its full time constant. It's never going to exceed its maximum capacity, and it's never going to discharge to its maximum capacity. And it's going to start out at 0 when I first apply this voltage to it. It's going to start out at 0, but then it's going to kind of stabilize out between these two voltages. And then it's either going to be taking in the energy, or it's going to be putting it back into the circuit depending on where my function generator is at. But when you're setting up your labs and stuff, make sure that you're setting it up for your 0 volts and your plus 10 volts. And then that time constant then is always based on what size capacitor I have or what size resistor I have in there. But these would be what I would get on my waveforms in my oscilloscope.
Would there be any application for having it done that way?
For timing circuits and stuff, the
way not charge all the way up to a full time constant. Would there be an application for that, or?
It's more of there are applications. I can't think of a particular application where but if we're doing it with for a particular timing, if we want to, the circuits become complicated on how we use these signals, but it's more to understand the signals and stuff. But there are times where if we're sending in a signal and we want to trigger off of a certain voltage, so we might want to trigger off of 6.3 volts. We might have a particular frequency, and then we want to just trigger off of. So let's just say, because it's always predictable. So let's go back. I'm trying not making this so complicated, but let's just say we went back to our full time 10 time constants on our signal.
Yeah.
And let's say that we had a circuit that we wanted to trigger off of certain voltages, okay? And we're going to trigger off of certain voltages because those are going to happen at a certain time interval. So if we're running in and we're running a circuit, and we know that we want to trigger our circuit after one time constant, we could go ahead and trigger at 6.3 volts, we would know that we'd be at one time constant. So we know that when my circuit gets to 6.3 volts going across either my resistor or my capacitor, depending on what type of circuit I have, I could trigger off that 6.3 volts and I know that I would be at 22 milliseconds. Okay? So then if I needed another multiple of that, I might want to trigger something off at 44 milliseconds. So then I would go at 86% and I trigger off that voltage at 86%. Okay? So they're trigger indicators, and it's a way that we can trigger off a voltage and know exactly what time it is. So it's kind of a time to voltage ratio. And so we're using it for triggering. But what we really want, so we're just kind of introducing this to us different types of signals and stuff, and what would I expect to see and stuff like that. Because as we get more into the circuits, then we can kind of see how we can set up triggers and stuff for it. Yeah, so there's applications for it because these are very predictable, and they're also used in our timing circuits. Let's see here. Yeah, but you'll see this. These are some pretty definite characteristics of certain signals that you'll see when you're using your oscilloscope. You also see that shark fin, you know that there's some capacitance in that circuit. If you also, you're measuring a signal and you see a signal like this, you know that it's an RC circuit. You know that there's a capacitor or resistor in there and that we're getting that discharge. And we can make these as what we call, we can make them as voltage doublers and triplers and stuff like that. So one application of where we take and we utilize these voltages is that if I'm running a microcontroller and all my voltages on my microcontroller, let's see here, let's see here. So if I have just a microcontroller, which is just an IC that I can program using, like a C++ language, these microcontrollers are going to be powered up by just a positive 5 volts. So my MCU. And then if we're talking to a PC, and we're using our serial communication, like our RS-232 communications and stuff, this RS-232 communication has both positive 5 volts and a negative 5 volts in there. Okay? Depending on how we're sending our signals, we might also send that serial communication and send it at negative 5 volts to tell it, hey, I'm ready to send. Well, my source voltage, all I have for a source voltage is a plus 5 volts. So let's just say we're running this thing off of a battery or something like that. Okay, so we don't have availability of a power supply where we can get both our positive and negative voltages. What I can do is, what the chips they call them are called MAX 232s. And what they do is they use what they call, they come up with an oscillator and they oscillate a signal at my plus 5 volts. They charge and discharge a capacitor. Then they come off the output of the resistor side to get the plus and negative 5 volts that we need for this. And so they call these charging pumps. Okay? They charge up a capacitor and then they pump it back in. That way, with just a 5 volt source hooked up to my microcontroller, I have the potential of being able to get my plus 5 volts and my negative 5 volts by just having a 5 volts applied to it. And we call those charging pumps. And they can be called voltage doublers, triplers, and so on. And you'll see one of them in your lab. There'll be a voltage doubler that you'll be, or voltage doubler that you're making in your labs and stuff like that. And so that's one of the applications of where we're using the, the capacitor and the resistor for a type of a signal. So this would here would be, for example, would be the RS-232. I only have a positive 5 volts. I can go ahead and get my plus 5 volts and negative 5 volts. Another application that you actually are using it right now is in your MyDAC. When you plug it into the USB, the only voltage we have is plus 5 volts coming from our USB and going into our MyDAC. But look at all the voltage that we get. We got our plus and minus 15 volts. And we also have our plus 5 volts. Okay, so we're actually multiplying our voltage. If you really look at it, we're putting only 5 volts into our microcontroller or into our MyDAC. But yet we have the voltage potential of 30 volts going to our plus 15 and our negative 15 volts. So that's one of the applications where you'll see it. They call those charging pumps. And they actually make little chips that we can just go ahead and it will automatically create an oscillator in there. It'll oscillate a signal going from 0 to 5 volts. It'll start oscillating. It'll start charging and discharging a capacitor. And then the output comes off of the resistor. And then they do some additional filtering and stuff like that to get it a little cleaner, more straight positive 5 volts and negative 5 volts. And then they can do that by incorporating another set of capacitors in there, and we can actually smooth out that ripple. And so that's one of the other applications of where we can use it. Another applications for RC, again, is just timing. If I just want to, Dominic asked me a question yesterday. We'll draw up Dominic's circuit here. So he asked about what would happen if I put the resistor in parallel with the capacitor. So before it was in series, now we'll put the resistor in parallel with it. That's their output. So we'll just say 10 volts going into our source. So when I first apply the power to it, my current is going to start to flow. The capacitor is going to act like a short, so I'm going to get some current division. Some of my current's going to go that way, and some of my current's going to go this way. And then those two currents are going to combine and go back into my source. Okay. So the instant I turned on we'll actually put a switch in here. So the instant I closed my switch, my voltage across test point A is going to equal what? 10 volts. Okay, so my capacitor is going to act like a short, right? So what remains constant in a parallel circuit? Voltage. Okay, so that really actually ends up shorting out my power supply for just an instant. I'm going to get 0 volts going across my test point A. Okay, then that capacitor is going to start to charge. Then once that capacitor charges up, then it's going to act like what? Like an open. And so it's going to have its full 10 volt source across there. And then the current going through my capacitor is going to stop. Now my current is still going through my resistor. I'm still going to get voltage going across my resistor. And so now what do I have for voltage going across from test point A now? With that capacitor acting like an open.
10 volts.
10 volts. Okay. So now, all of a sudden now I open up my switch. And that first instant when I open up that switch, and I remove my power source, my capacitor is going to act like its source now. And so that instant when I open up the switch, what do I get at my test point A?
10 volts.
10 volts. I'm still going to get my 10 volts yet. And then what's going to happen is that current now my capacitor becomes its source, and the current's going to flow through here. My polarity across my resistor didn't change this time. So over a given amount of time then, depending on what my capacitor size and what my resistor size is, I'm going to still get my 10 volts even after I opened up my switch. I'm still going to get my 10 volts, and then eventually that capacitor is going to discharge, and then I'm going to go down to 0 volts. So we can use this for a timing circuit. So what this is that we just made an off-delay timer, okay? And it depends on what the capacitor and the resistor values are. It's going to determine how long I'm going to have that off-delay for. And we have to, so it's going to start out at 10 volts, and then it's going to just slowly discharge, and then shut off after a given amount of time, and it's going to drop down to 0. So this is what we would call an off-delay timer. So I close my switch. After a certain amount of time, that capacitor is going to, now remember this capacitor here, this capacitor is going to charge up to 10 volts just like that, right? Because there's no opposition to current, there's no resistor in this charging up this capacitor, so that capacitor is going to charge up almost instantaneously. The only RC time constant that we have in here is the resistance of the wire and the capacitor. And so realistically, that capacitor is going to charge up to 10 volts just like that. So I close it, I'm going to get 10 volts coming out of my output. I open up my switch, and over a given certain amount of time, then that's going to remain 10 volts for a certain while, and then start slowly dropping. So if I had a very large capacitor here, and a very large resistance, I can maintain that 10 volts for, I can maintain that resistance for, or that voltage for, minutes if I want, depending on how large this capacitor is and how small this resistor is. So if I had let's say if I had something to say, 1,000 microfarad capacitor, so we'll say 1,000 microfarad capacitor, and let's go with a 10 meg ohm resistor. What is one time constant going to equal?
Seconds.
How many seconds?
10,000 seconds.
10,000 seconds. So that means that I'm going to maintain my output voltage from a plus 10 to a plus 6.3 volts for 10,000 seconds. Or how many minutes would that be? What is it?
166.7 minutes.
166.7 minutes. Okay? So after I open up that, so let's just say that my level, I can have a level range of anywhere from a plus 10 volts to a 6.3 volts. As long as I'm within that range, we're going to consider my output to be high. So when I open up that switch, my output's going to stay on for 166.7 minutes before it goes to a low. Yeah, and so that's my off delay. I turn it on, I'm going to get my voltage right away. It's going to go up to 10 volts. I open up my switch, and then after 166.7 minutes, my voltage is going to, then we'll consider my output to go, to turn on. And depending on what that range is, I could even actually say that my acceptable output range could be 10 volts to 3.7 volts. Depending on what what I want for range, I could go multiples of different time constants for that. So those are some of the applications that we use for RC time constants and stuff like that. So we can make on delays, off delays, you know, depending on if it's in series or if it's in parallel, however it is, we can come up with different circuits using, and that's all our timing circuits.
Kurt,
Yeah.
on a cell phone, usually after 2 years, your battery starts to die like every 5 hours because it doesn't hold a charge. Is it because the battery's actually dying or the capacitor's dying?
Actually, because of the batteries dying.
Okay.
Yeah, that's the battery. It's the chemical breakdown on the battery is starting to isn't able to maintain the charge anymore. But that's because that's the chemical breakdown that's happening with the battery.
So if you're ever charging a laptop and unplug the power supply and it stays on for like 10 seconds, is that because of the capacitor?
That is because of all the filtering in there. Yep. So like, well that's like on, well a good example of it is if you have, like if you have a stereo, a receiver and stuff, did you ever notice that on, I think in